Let me get started. Hello students. So in this particular lecture, we will take a look, we will dwell into more analysis of those currents. So what does that really imply? Right, so what we had got was the IDS short channel linear current, and then the IDS short channel saturation current. So let me pick up a pointer so that it will be easier for me to direct where I am pointing to. So we have got the linear current, which is defined on this left hand side. So this is the linear current I'm talking about. So this is what we had derived. Of course, we derived it in two ways. One is for our own easy understanding, as well as one from the Chaudiny's paper, which helped us to derive this particular expression. And then the short channel current for the saturation region. So on the left hand side we have the linear region. On the right hand side we have the saturation region. We also wanted to know what is the exact VDS saturation, right? In the long channel model, we know that VDS saturation or the current reaches the saturation when VDS value reaches VGS value, whatever is the VGS values minus VT. Right? In this particular case, that may not be the case. The current in the shorter channel transistor, in the channel length, if it is shorter, then the current actually can get saturated much earlier than that of the VGS minus VT. Right? So to arrive at that particular VDS saturation expression, what we do is very similar to what we had done for the long channel. Equate these two current expressions, because we know that the current profile is still continuous for the linear region as well as for the saturation region, and that particular point where it does the transition from the linear region to the saturation region, both the expressions should be equated, or rather both the solutions for both the expressions should be the same. So in that sense, if VDS saturation, if I put VDS in this particular expression and then the VDS in this particular expression, which written to be as VDS saturation, then we will arrive at this particular expressions of VDS sat, right? Which is nothing but in the last slide I had said, in the last lecture I had said, it is we can say that it is a parallel combination of VC and VGS minus VT, right? Where VC is the critical voltage. Critical voltage, if I draw the profile of the velocity, and if I draw the profile of the electric field, lateral electric field, EDS, remember it is not a vertical electric field, it is still the lateral, which is EDS. Vertical electric field is nothing but gate to source. The lateral electric field is the drain to source. Right, so this vertical profile, what we had seen was somewhere here. For an NMOS, it will go to 10 raised to 7 centimeter per second. So this particular value is our EC, the critical electric field, multiplied by L will give me the VC value. So somewhere here, I'll just write it down, EC multiplied by L will give me VC. Right, so that is what the VC is. Right, so this VC is what we are taking it here in our expression. Right, so this VDS saturation is now a function of VC as well as VGS minus VT. Kind of very important expression, and we will look into it in more detail. And if you remember the saturation current, if I write the saturation current for the short channel, so I'm writing it for the short channel. It was nothing but WC oxide velocity saturation, right? And then multiplied by our VGS minus VT, and then we had VDS saturation, right? So if I put this VDS saturation as nothing but the parallel combination of VC and VGS minus VT, right, we will arrive at this particular expression. Now this just for the simplification, this VGS minus VT, we have taken it as a term VGT. Okay, so that's what so this particular expression is nothing but WC oxide V saturation and VGS minus VT the whole square divided by VC plus VGS minus VT. Okay, hope this is clear to everyone. Right now, if I have, if I consider the previous expression, so if I consider this particular expression, VGS minus VT, especially take out this particular term. The other three terms or the other three variables, W, C oxide, and V velocity saturations, are basically a constant parameter. It's not going to change. It's not going to change. So if I consider VGS minus VT divided by VC plus VGS minus VT. So if I consider that, all right, so I'm going to write it here so that we have this VGS minus VT, the whole square, and then divided by VGS minus VT plus VC, right? So if I have this particular term, and let's say that if VGS minus VT is very, very smaller than VC, so I'm considering, say there are two potentials, potential difference, which is one is the parameter VC, the critical voltage, another one is VGS minus VT. And if one is smaller than the other one, if the other one is smaller than the first one, then what is likely to happen? So how can we approximate the current term? So if VGS minus VT is actually very, very smaller than VC, right? So I can actually ignore this particular term, right? So what is left in the denominator is only VC. So I will actually get WC oxide velocity saturation multiplied by VGS minus VT, the whole square, divided by VC. Right now, again, this is nothing but a square law. Right, so if I consider IDS in square law, in the sense the current expression is a function of the square of VGS minus VT, the whole square, right? Turns out to be very, very similar to our long channel saturation current. Okay, and if it is the other one, the VC, if it is very, very small than that of the VGS minus VT, then we have WC oxide. So if I consider in this particular expression, if VGS minus VT is very, very large and VC is very, very small here, so I can actually cancel this particular term with that of one particular term in the numerator side. So we will get VGS minus VT. So finally, my expression, approximate expression, turns out to be this one. Right, so it is not a square law. In fact, the current is directly proportional to VGS minus VT and not the square of VGS minus VT, and that's why I've written it like a linear law. So if I really look into this particular parameter of the current in both these conditions, like VC when one is very, very smaller than the other one, what it really implies is the current is actually attaining the saturation, the saturation, the current becomes constant value because of the one which is lower. All right, so let me pick up a pointer. Okay, and then that's it. So if VC is actually very, very small, then the current is actually, the saturation current is actually determined by the velocity saturation region. If it is the other case, VGS minus VT, then the current is actually determined by the VGS minus VT and not the velocity saturation. Right, what it really implies is the first one, if VGS minus VT is achieved earlier than that of VC, right, then VGS minus VT, we will anyways reach the pinch-off region, right? So if you recollect the pinch-off region, what it really means is the gate to drain doesn't have a voltage. So the VGD value is actually less than 0.3 volts. So that is where the channel that, it starts from the source to the drain. So there is no channel that has been formed at the drain side. So that is where the pinch-off region is, that is why it is called as a pinch-off region. The channel is absent at the drain side, and thereby we get the saturation current. So if VGS minus VT value is actually less than that of VC value, then the current attains the saturation due to the pinch-off region. Right, very, very, very similar effect to that of the long channel model which we have seen. The other one is when the VC is actually very, very small, the velocity is likely to attain the saturation because of the velocity saturates at the critical voltage, at the critical electric field, which we can, arrive at the critical voltage, and not due to the pinch-off region, right? So the pinch-off region, it touches the pinch-off region at a very high voltage in the second case, but it has, the velocity is anyway saturated, and thereby the current gets saturated, right? So these two conditions are kind of very important to proceed further. Okay, so this particular slide, I've drawn two profiles. One is the velocity profile with respect to VDS, and then another is the current profile with respect to the VDS. Right. So how do I do this particular VDS? It is nothing but EDS multiplied by the channel length. Right. So that's how I have drawn this velocity profile with respect to the VDS. In fact, one can actually draw the velocity profile with respect to EDS, and in the x-axis I can just multiply by the channel length and I'll get the VDS value. Right. Now let's, we will anyways, we have derived this value of the VC. We have derived this VC value, which is 1.01 volts for the NMOS. So here is an example of only NMOS. So I'm just, this particular profile, what I've drawn here, the velocity with respect to VDS, and then the current with respect to VDS. Let's say that this is for the NMOS transistor. And VC is equal to 1.01 volts. That is what we had derived. If you remember the last time, we had the effective mobility of the NMOS transistor reaching around 96 value, 96 or 97 values. And then the channel length was 50 nanometers. VGS applied was 1 volts. VDS was, I don't think we'll require the VDS for finding out the VC critical voltage value. But let's say that for the NMOS 65 nanometer technology, VT is 0.3 volts and VGS that has been applied is 1 volts. So we know the pinch off effect, if VGS is 1 volts and VT is equal to 0.3 volts, the pinch off effect or the pinch off region or the channel that gets missed at the drain side, it will be achieved when we have VDS value is equal to VGS minus VT, when VDS value attains 0.7 volts. All right, so this is that particular point. So that's why this VGT is nothing but VGS of 1 volts minus VT of 0.3. So it is achieves 0.7 volts. Right, the same thing here, VGT, it is nothing but VGS minus VT. This is where the pinch off region is achieved. Right, so this represents the point B in the velocity profile. This represents the point B in the current profile. Okay, and let's say the critical voltage which we have calculated is 1.01 volts. So what it means is that 1.01 volts here at this particular point, point C is achieved where the velocity is transitioning from the linear current to the saturation current. Right. Similarly, here on the counterparts on the current, what we have drawn is from point C, it is nothing but anyways the saturation region. Right. If you remember this point C, for deriving the current expression in the short channel model, accommodating the non-ideal behaviors, we had taken the velocity saturation. Velocity saturation, that is nothing but the point C, which is 10 raised to 7 centimeters per second. So we have directly taken this velocity saturation value in deriving the current expression for the saturation current. Right. So we got two voltages here. So basically we got 2 points B and C. We got 2 points B and C. And remember this point B in the velocity profile, it will always be, it will lie in the linear profile for the velocity. Right, so point C is where the saturation, the velocity saturation starts. Point B is where it is still behind the saturation point. So point B is somewhere lies here, where it is nothing but it is the point where VDS is 0.7 volts. The third point in this particular profile is VDS saturation, which is nothing but VC in a parallel combination of VC and VGS minus VT. So if VC is equal to 1.01 volts and VGS minus VT is 0.7 volts, if we do the calculation, we will get VDS saturation point as 0.41 volts. Okay. So if I want to draw those that particular counterpoint in our profile, VDS saturation, that is the point A here, or VDS saturation is nothing but 0.41 volts, and if I take that particular point, the point A in the velocity profile represents the x-axis as 0.41 volts. Right, so that is a point A in the velocity profile, and similarly the counterpoint in the current profile is drawn here in the point A here. So now I have drawn point A, B, and C. And of course, I've just connected those points by a line, and also I have the line after the point C and a line before point A. Right, so just to complete the velocity profile and just to complete the current profile. Now it is very interesting to see here is the velocity here. The first point is the velocity here saturates at point C. The current also saturates at point C. Right, so that is very self-intuitive to understand. Once the velocity saturates, I think the current also saturates. So at this particular region, after the C, right, there is no, after this particular point, what I'm talking about, there is no, so there is no argument in that sense, right? So if the velocity reaches the saturation, the current also reaches the saturation, okay? Okay, let me take another point here, another color. And let's say that this, starting before point A, the velocity is in kind of a linear profile, and thereby even the current is in a kind of a linear profile. All right. So our whole discussion should be in this particular region of A, B, and C, right? A to C. Okay. Let's pick the point B. So I'll pick one more pointer here. Okay, that's what I have done. Okay. And let's pick this point B. So that is the counterpoint B in the velocity profile. So this particular point B is, if I look into the velocity profile, it looks like a linear profile. Slightly away from B, slightly below and above B, it still follows a linear profile in terms of the voltage, in terms of the velocity. But whereas the current profile says that it is nothing but a saturation current. And it makes sense because this point B, if I look into the x-axis, it is nothing but VGT, which is nothing but VGS minus VT. So point B, if I want to, if it is still, the velocity is still a linear profile at point B, that means that, if I increase the VDS value or the electric field, the lateral electric field, the velocity is going to increase linearly. But what happens is the transistor has already reached the pinch off region. So VGS minus VT, the pinch off region has already reached. And thereby after that, you will never going to get a more increase in the current. So the current actually reaches the saturation, right? So that's where this point B, we can draw a straight line connecting to the C. So the point B onwards, we know that it will be a saturation current because it is anyways the pinch off region or the saturation region, right? So we are left with this particular region between A to B. So let me consider another color. Okay. So between this particular region of A to B, all right, between this particular region of A to B, right? So in the current profile, it says that it reaches saturation, right? The current profile, it reaches saturation not at C, not at B, but it reaches saturation at A, right? It reaches saturation at A. That means the straight line starts from point A, right? Although the velocity profile is still a linear profile from A to B, right? In fact, before A also, it was a linear profile from A to B. Right. So what it really implies is from between A to B, it reaches the saturation. That means starting from point A, the moment point A is reached, right? Point A in the sense, if VDS, the applied VDS for a VGS of 1 volts, right? If VDS achieves 0.41 volts, right? My current will be saturated. Right, what it really implies is the saturation current in an NMOS, which is actually short channel transistor, which is actually a short channel transistor, or according to the short channel model for the NMOS transistor, the saturation current is attained much earlier than the VC and also the pinch off region, which is VGS minus VT. So it is attained at point A and not at point B or C. It is attained much earlier, that is at point A. Okay, and the reason or the empirical reason that is being given for the point A onwards is that the effect of the current, the current is going to flow, or rather the majority carriers that is going to flow from the source to the drain side will have a multiple effect. One due to the, if the point A is actually very, very close to point B, or rather 0.41 is closer to 0.7 volts. So the channel at the drain side is also decreasing. That is one region. Although it has not reached the pinch off region, it is kind of decreasing. The second thing is, it also has an effect of the critical voltage, where the velocity, although point A is kind of away from C, but it is closer to C in terms of the other points which are below A. Right? So in that sense, point A is also kind of closer to C. So there is a kind of tendency of the velocity ceases to increase as the electric field increases, as the lateral voltage increases. And thereby we can say that the point A is nothing but the dual effect of the velocity saturation as well as the pinch-off effect, and that is where the current will start becoming or attaining the saturation value. Okay, hope this is clear. Right, just to summarize, the ideas short channel which we have actually derived is nothing but the WC oxide VGS minus VT minus of. So this is what our general equation was. V of x, the voltage at any point in the channel, and then the velocity at any point in the channel. Right, so we had used this particular expression. And just to summarize, at all the points A, B and C, the current is still the same. Right, below point A, it will be the linear current. So I should write actually the linear expression below the point A. After point A, starting from point A, all the currents, A, B and C currents will be the same. And if I look into this particular expression, it is nothing but WC oxide VGS minus VT minus VDS sat multiplied by the velocity saturation. So this should be velocity saturation. Right, velocity saturation. Right, so if I look into closely into this particular expression, right, this is nothing but VGS minus VT minus VDS saturation. All right. Now, point A, B, and C, all of them are giving me this particular expression. So VDS saturation is basically a constant value, which is nothing but 0.41. That is, which is defined for now from where we have defined a point A. B point is where it is actually VGS minus VT. C is the point where it is VC. Right, but point A is where the VDS minus VDS saturation, which is nothing but the parallel combination of VC and VGS minus VT. Right, so once it attains point A, B and C are all the same value. So the current actually attains the saturation value. Now again, if I look into this particular expression, normally in the long channel current or even in the short channel linear region current, we will always get an expression of the current as a function of VGS minus VT minus VDS by 2. Right, and here we have VDS saturation or basically VDS value. Now VDS is nothing but a VDS saturation value, which is nothing but VC and a function of VC and VGS minus VT. So ideally it should have been VDS by saturation by 2, ideally. Right, so if it is actually VDS saturation by 2, this particular value VGS minus VT minus VDS saturation by 2, right, it will be more, right, it will be more than that of VGS minus VT minus VDS saturation. Right, so if I take out this particular value, take out this particular 2 somewhere away, so that I can actually so VGS minus VT minus VDS is actually a lesser value than if it is VDS by 2. All right. So this particular value, if I actually compare this particular value or this particular value or this particular value, it is actually less than that of VGS minus VT minus VDS by 2. It is actually very well compensated by this velocity saturation. Right, so at point A, so if I go back to the previous profile of velocity, at point A, I know this, the value, the point A here is where the current saturates, but point A here, the velocity is not actually velocity saturation. right? It is less than the velocity saturation. But now in this particular expression, we are taking it as velocity saturation. And the reason is actually it is compensated well by this VGS minus VT minus, in fact, it should have been VDS saturation by 2, but that's kind of getting compensated here. So we take a higher value here so that this whole expression is actually a less value, so that gets compensated, right? Of course, you don't have to, don't have to really appreciate this particular effect, VGS minus VT minus VDS saturation, whether it is VDS saturation by 2 or this is the correct expression, VGS minus VT minus VDS saturation multiplied by velocity saturation. But just for those of you who are interested in why it is actually not VDS saturation by 2, because we have taken a higher velocity term, that's why we are getting compensated at VDS saturation.